The next thing is eigenvalue decomposition. Given a linear transform by a matrix A, and any points on an eigenvector V will remain on the same direction, while its magnitude is multiplied by a corresponding eigenvalue. So these statements can be summarized by these simple equations. A times V is lambda times V. So A is matrix and V is vector, and lambda is a scalar corresponding to the magnitude, and V is the vector. So when we apply a linear transformation to a certain vector, then we will get a new vector. Okay. For example, let's assume that if A is a square matrix and we are in the same space, then when we apply a linear transformation A to X, then let's say this is X. Then after applying by applying transformation, then we might have Y around here. So usually this is a usual case, but there are some special vectors, and for those vectors, when we apply a linear transformations AV, then the result is lambda V. It means it doesn't change the direction, it just changes the magnitude. We have V, vector V, and after applying a matrix A, then the result is lambda V, which is something like this. We just change the scale, not the directions. So this is quite important, and we will see how we can use this property in the next slide. So here's the simple exercise to check if you understand this eigen decomposition and eigenvalue and eigenvectors. So if two eigenvalues are equal, let's see, we have eigenvalue lambda, then any linear combination of the two eigenvectors is also an eigenvector with the same eigenvalue. Let's say a v is lambda v, and a u, let's say v and u, they are eigenvectors, but they share the same eigenvalue. Okay. Then any linear combination of the two eigenvectors is also an eigenvector. So let's try. V plus mu is actually a v times a mu is lambda v plus lambda mu is lambda v plus u. Okay, so if we have any weights here like alpha, beta, alpha, beta, alpha, beta, alpha, beta. So any linear combination of the two eigenvectors is also an eigenvector. This is an eigenvector. Look at this one. Let's say this one is, let's k, then ak is lambda k, right? So k is a linear combination of the two eigenvectors. So by this equation, we can say, oh, k is eigenvector with eigenvalue lambda, which is the same as this. Okay. Then how can we use this eigen decomposition for computation usually? So as I said, we can have some multiple eigenvectors. When the A is 3 by 3, then we can have 3 eigenvectors and 3 eigenvalues. So we can have this. Actually, mu is something like eigenvector 1, eigenvector 2, eigenvector 3. So u is a matrix with eigenvectors. And the lambda is a matrix. V1 is a vector here, right? So it is a matrix. Lambda is a matrix where all the diagonal elements are eigenvalues. So lambda 1, lambda 2, and lambda 3. And the other off-diagonal elements are zeros. Okay. So when we have three eigenvectors and eigenvalues, then we can represent all of them in a single equations. Okay. Then these eigenvalues are orthogonal. Okay. And if we multiply U transpose here and here, then we can get this one. So this is really interesting. Let's say we are multiplying A like this, then we don't have to multiply A twice. It's mu lambda square mu transpose. Why is that? Mu lambda mu transpose mu lambda mu. Actually, A, this one is A and this one is A. Mu transpose U transpose U is actually identity matrix, and the lambda is a diagonal matrix. So this one goes to this, and then yes, we have. What about A to the power of K? Then mu U times lambda to the power of K times U transpose. So when we calculate the power of A, then it's really simple. The calculation is really simple. And when we calculate the inverse of A, then also it is simple. We don't have to calculate, we don't have to use the inverse definitions. So we just, if we have eigen decomposition already, then this is the inverse of A. So lambda inverse is really simple. Lambda inverse is 1 over lambda 1 and 0, 0, 0, 0, 0, 0. 1 over lambda 2, 1 over lambda 3. So simple. So computationally, it's really cheap. Okay, element wise, we can understand this equation in this way too. And when we calculate the determinant of a matrix, then if we have an eigendecomposition, then it's simple too. Look at this one. Determinant of A. Determinant of A can be calculated really simply. Determinant of A is determinant of U lambda U transpose is determinant of U times determinant of lambda times determinant of U transpose. And since U is orthogonal matrix, then determinant of U is 1. And this one is 1. So it is determinant of lambda. And in this equation, in this matrix, we don't have any off-diagonal elements. All the off-diagonal elements are zeros like this. So determinant of this matrix is simply multiplication of all the lambdas. So once we have an eigendecomposition, then determinant of the matrix is really simple. Just multiply all the eigenvalues. And the trace of A is also simple. Trace A. Trace A is U lambda U transpose. When we calculate trace of matrix multiplication, then we can actually rotate. So TR trace U transpose U lambda. And that one is actually trace lambda because this one is identity matrix. So think about this lambda. We have eigenvalues on the diagonal as a diagonal element. So trace lambda is sum of all the eigenvalues. That's it. Determinant is the volume change. So look at this equation. When we transform X by matrix A, then we can rewrite that based on the eigendecompositions. And matrix U is orthogonal matrix, which means when we apply a matrix U to X, then it is rotation or reflection or permutation. So basically we don't change the volume, we don't change the scale of X, we just rotate. Okay, and U and U transpose, they have inverse relationship to each other. So let me put it in this way with the two-dimensional example. So let's say this one is X, and when we apply U transpose, then we can have Y. Okay, this is Y. Basically, the scale of Y is the same as the scale of X. And then we multiply eigenvalue matrix. So in the two-dimensional space, it is lambda 1 and lambda 2, and we multiply matrix vector Y. And if we multiply this one, then we can get lambda 1 y1 and lambda 2 y2. Okay. After multiplying lambda 1 and lambda 2, so we change the scale. So y has lambda y1 and y2, and by multiplying lambda 1 and lambda 2, actually we multiply y1 to lambda 1 y1 and lambda 2 y2. Then actually we changed the vector. And after changing this scale, then we rotate the vector back. So from this, we got this by ut. Then by u, actually we have to this back. So now we have this one. Okay, so the volume change is affected by only this one, lambda. Okay, and look at this one. When we change the volume from this one to this one, actually we multiply lambda 1 and lambda 2 in this direction and this direction respectively. So if we calculate the area, then lambda 1 and lambda 2, lambda 1 times lambda 2 is actually changing the area. So the determinant of A is determinant of lambda matrix, which is actually multiplication of lambda 1 and lambda 2 in the two-dimensional space example. So I just to show you that lambda 1 times lambda 2 is actually the changing of the volume, the changing of area in two-dimensional space, which is actually the determinant of A. Okay, so this is quite important message. Determinant of a matrix is the volume change of that matrix transformation. And the next one is that the rank of A is related to the eigenvalues. So when you read some machine learning papers, then they say, okay, so this matrix is full ranked, or this transformation is full ranked. So especially in the neural network, in deep learning, the transformation is based on the matrix, and then they can say, okay, so this transformation is full ranked. It means there is no zero eigenvalue, because if there is a zero eigenvalue, then the rank is less than its dimension. Okay, so you might see this a lot when you read the papers. Okay, next, A is symmetric. If A is symmetric, then if two eigenvalues are different, then they are orthogonal. So let's prove it. So symmetry means A transpose is the same as A. Then we have two eigenvalues, different eigenvalues. So let's say we have AV is lambda 1 V, and we have AU lambda 2 u. Okay, so we have two eigenvectors with two different eigenvalues. Okay, then we can multiply the same vector here and there. So we have a u transpose a, v is lambda 1 u transpose v. Okay, and then if you look at this part, then that is actually lambda 2 u transpose and v, lambda 1 u transpose v. So we already know that the lambda 2 and lambda 1, they are different. And then to make this equation valid, then this part should be 0. Okay. So u and v should be orthogonal. Okay, that's it. And then the next, if a is positive definite, then all eigenvalues are positive. So positive definite means for all vector x, this should be positive. Okay. And then with this matrix A, then we can apply the eigen decomposition. So we can think of x transpose u lambda u transpose x. Okay, so this is positive. Okay, then we can think of this one as y. Then we have y transpose lambda y. So in this case, we can rewrite this equation with the element lambda I times yi times yi. Okay, because this is a diagonal matrix. Okay, then if any of these lambda I is less than 0, then we can make this sum to be negative with the specific y vector. For example, if lambda 1 is minus 1, and lambda 2 and lambda n, maybe they are some positive numbers like 2 or 100, it doesn't matter. Then when we have specific y, like 1 and 0, 0, 0, 0, 0. Okay, so if this is y, then so lambda 1 times y1 is minus 1, and all the other element, lambda 2 times y2 is 0. So all the others will be 0. So in total, this is negative. Okay. So if we can make any specific y vector for this equation, then we can come up with a specific x to make a specific y. So it means if A is positive definite, all eigenvalues should be positive. All lambda I should be positive. And the next one is Cholesky decomposition, which is really efficient matrix decomposition, but I don't think we should cover all these equations. But this is another important decomposition, so please study by yourself if you want to go into machine learning or deep learning. Okay, then there is application. Okay, and then next one is vector and matrix derivatives. And we already talked about the function derivatives, right? So the derivative of a vector or a matrix with respect to a scalar is simple. So A is a vector. Then when we take a derivative of this A with respect to x is a scalar variable, then this one. So this is actually a vector, and each element of the vector is this one. And if B is a matrix and we take a derivative with respect to a scalar x, then it is a matrix, and the element at ij is this. Okay, that's quite simple. And the derivative of a scalar with respect to a vector or matrix is actually exactly opposite. So this one is a scalar, this one is vector. And this itself is a vector, right? And the element at I of this vector is this one. the derivative of x with respect to a sub I. Okay, likewise, we can take a derivative of a scalar with respect to matrix and more. When we take a derivative of this inner product, then the result is A. So it's something like this one, AX, right? When A and X are scalar values, scalar variables, then this one is A. Likewise, so we have X transpose A, where X is vector and A is vector, then still, when we take a derivative of this one with respect to X, then it's A. Okay, and when we take a derivative of A times B, then it's like a function compositions. Okay, so take a derivative of A and times B plus A times derivative of B. Okay, and the derivative of A inverse is simply like this. And the proof is not that complicated here. Proof. Okay, A inverse times A. Okay, then we want to take a derivative of this one with respect to x. Then we can use this one. And derivative of A inverse, derivative of x times A plus A inverse times derivative A x. Okay, then look at this one. This one is actually identity matrix. So this one is a 0. Then this one is we can rearrange this equation. Then x A inverse is minus A transpose, minus A minus A inverse and A x times A inverse. Okay, so you can get this one. Okay, and then we can take a derivative of trace operator with respect to A, then we can get BJI. So it's kind of transpose. And we can take a derivative of trace of A times B with respect to A, then we get A transpose. Okay, and also when we take a derivative of determinant of A, then the result is determinant of A times A inverse transpose. Okay, this is pretty much all we need for, actually this is a little more than we need, Okay, so basically I'm done, but there are some students who are confused with these total derivatives and partial derivatives. So let me explain what's the difference between these two. Okay, given a function f, which is ax plus by, and if we calculate the total derivatives, then we don't ignore the relationship between the variables. So derivative of f with respect to d is a plus b times dy over dx, because x and y are kind of connected. But in partial derivatives, we don't care. So x and y, we just assume that they are independent. Okay. So when we take a derivative with respect to x, then this is cancelled, right? Because x is independent of this term. So the partial derivative result is a. It's quite simple. And in In neural networks, we use lots of derivatives, and in that case, we just use partial derivatives. So if you get confused in machine learning, okay, then we don't use total derivatives that much, okay, especially in neural networks. Most of the time, we use partial derivatives, okay. Partial derivative in this one, not this one, okay. We use this one. And there are different notations for total derivatives. df over dx is the same as f dot or df or f dash. Okay, so there are different notations meaning the same things. And delta is change of variables, how much they changed. Okay, and del or nabla is gradient operator. Okay, so they look similar, but they are different things. So if you have any more question, email me.